So, welcome everyone to this meeting of the virtual CICS user group. I'm Trevor Eddles. I'm the CEO of iTechEd Limited. We're a mainframe consultancy, analysis and technical authoring organisation. We're the people responsible for the content on the virtual CICS website, and we produce the newsletters. We also look after the virtual IMS user group as well. Okay, so let's start by running through the agenda for this meeting. As usual, most of the meeting will be taken up with a presentation, and today our guest presenter is Eugene S Hudders. He's president of CICS Corporation, and his presentation is called LSR Tuning Today. And a copy of the slides from the presentation will be on our website later today. If you missed our previous meetings, you can download copies of those presentations from our website. And you can also listen again to the whole presentation. There's a link on the resources page of the user group website. If you haven't been on our website, then it's fundi.com/virtual-CICS/resources.htm. Following Gene's presentation and any questions you have for him, we'll move on to the latest CICS news and the latest CICS related articles. Feedback request is there to remind me to ask you for your feedback about this virtual meeting, and then I'll tell you something about future meetings and some other stuff today. So that's the plan for this meeting. I'm anticipating that it will last for a little over an hour. Okay, as I just said, today's presentation is from Eugene Hudders. Gene is president of CICS Corporation, a company that develops CICS, which is a performance and problem determination tool for CICS. He's worked on IBM mainframe computers for over 50 years. He's made presentations about CICS and VSAM at technical conferences such as Share, CMG and WAV. And in addition, Gene has written several books on CICS and VSAM in the areas of problem determination and tuning. So what I'm going to do now is hand over control to Gene. So let me just do that now. Okay. So now, Gene, you should have a message saying you're presenter.
Okay. Screen, here we go. And okay, well, good afternoon or good morning, depending on where you are. My name is Eugene Hudders. I'm from CICS Corporation, as Trevor mentioned. I'll be talking to you a little bit about LSR tuning, and specifically from a today point of view. There are some things that are associated with, the LSR itself, which is the part on the VSAM part, which some of the things that you can do to improve VSAM, you would have to go through the DFSMS part, because there are some important things that you can have available in that area. I will try to just touch a couple of the things that will affect you from an LSR point of view. There are some, as usual, there's some disclaimers. Remember that I'm going to be showing you a couple of things as far as some benchmarks, but your mileage may vary. So that's something that you have to look at. You have to do those benchmarks yourself to get your own, feedback as such. And you also have to remember the political factor. And many times you want to change something, but the boss, has the attitude that says, if it ain't broke, don't fix it. So, you have to, sort of take that into consideration. And again, as usual, I'm going to be talking about products which belong to IBM. And, these are more or less some of the things I'll be mentioning. If you have any questions, just send them, and Trevor will interrupt me and let me know what it is. The presentation is going to cover basically several areas. One of the things, just a plain introduction, just to talk to you a little bit about CICS LSR. But specifically, I'm going to spend a lot more time in this section talking about what a physical I/O is, what the sequence of instructions or events, and I'm going to look at it from a very high level. I mean, it's not very specific, but just to give you an idea of how much CPU time you're going to spend whenever you have one of these, you do a physical I/O out to the disk. Then I'm going to go into the LSR tuning. And the first part of it will be, just some of the traditional things that we're doing today, some of the things that you normally do, okay? After that, we're going to go into other areas in LSR tuning, which include things like fragmentation and number of LSR pools and so on. And finally, we're going to hit some hidden tuning areas, which are more VSAM oriented, but they affect your LSR, pools and so on. So, and with that, we should cover, just about a little bit less than an hour. Okay. Okay. The CICS basically supports VSAM, or, in three ways. One is non-shared resources. The second is local shared resources. And the last one is RLS, record level sharing. From our perspective, we're going to be spending most of the time or all the time in LSR. You really understand why you have a file in NSR. There may be some valid reasons, but I'll cover a couple of them at the end of this chapter, at the end of the presentation. But in general terms, most of your files are going to be either RLS or LSR. RLS if you're going to be sharing it across the plexus and so on, Plex, and LSR within your own CICS region. The big difference between the three is who owns the resources. In the case of an NSR, the resources belong to the file itself. And whether the resources are being used or not used, no one else can use them except that particular file. In the case of LSR, the resources are shared between the files, so that if one file is not using, its resources, somebody else can use them. That's a tremendous advantage, and it gives you a better performance in NSR. Benchmarks that we have run, we normally can see LSR up in the 90% look-aside, while NSR will range in the 40 to 60%, even though, you can get some NSR files out in the 90% also, but the vast majority of them will be in the 40 to 60% range. And in RLS, the owner of the resources are not really within CICS. They're out in another address space called SMS VSAM. And that, for RLS, you require the coupling facility to be able to work with. In general terms, as I mentioned, you should try to run either RLS or LSR for your files. Okay, now what are some of the advantages of LSR? Well, one of the things is a more efficient use of virtual storage. As I mentioned, you can have a file that, you define as NSR, you gave it 20 strings and you gave it X number of data and index buffers. And if during the period of the day, that file, let's say, is used very heavily early in the morning and is not used the rest of the day, well, those resources are tied up and nobody else can use them. Meanwhile, if you had that file in LSR, the LSR would allocate the resources that are required for that file. And when that file is no longer used, well, the resources can be used by somebody else, specifically the strings and the buffers themselves. Again, one of the better things of LSR is that you can store your sequence set indexes in the buffer pools, and it gives you a better side than you get with NSR. And NSR uses a least recently used algorithm, which is a very good algorithm, and it tends to be self-tuning, and then the larger the LSR pool is, the better the LRU algorithm works. Again, you only have one copy of the CI, and that can cause a small problem in some cases where you may have to remain in NSR, such as if you do a start browse, read next, read next, read next, and then you say read for update without ending the browse. That's going to cause a problem in LSR because you only allowed one copy of the CI. And what will happen is you'll probably cancel with an AFC something, AFCG, I think it is. Another advantage you have with LSR, which the limit is basically how much virtual storage you have, is you can allocate up to 255 pools to be able to segregate your files. However, you really don't get much of bang from the point of view of performance unless you're using VSAM thread safe, okay, which will allow you to have accesses to separate pools at the same time. Otherwise, if you have 8 pools and they're not VSAM thread safe, you will access these pools individually because you're going to be tied up on the QR TCB. Okay. And again, one of the things I didn't mention is, but LSR and RLS have been the latest IBM announcements over the years have been oriented towards that. Okay. Okay. Now, this is an area that I'm going to talk a little bit, for it, because I think it's very important that you understand, or we understand what's involved in a physical I/O. Why we don't want to do any IOs that involve going out to the disk drive. Okay. There's a lot of instructions that occur between when you start in your application, you issue your execute CICS read, for example. It goes into CICS. From CICS, it goes to VSAM. From VSAM, it goes to MBS. And, and that a lot of instructions that are executed. But in addition to that, you have something called a state change. Anytime you have an interrupt, you have to repopulate your translation look-aside buffers. And you have to also, some of the caches also have to be repopulated. So, what happens is, depending on the models, now the older models, it can be up to an 8% loss versus the newer models, which IBM has rewritten some of the code for the virtual storage part. It can be down to about 3%. So what it really means is, if you have a 100 MIP machine, you could all of a sudden, when you have a state change, be running only at 92% or 92 MIPS instead of 100 MIPS. Now that's, something which is temporary, and that's something which is expected, because, you're always going to have interrupts in the system. But if you can reduce the number of physical IOs that causes state changes, you'll be able to get better performance. And one misconception which I hear every once in a while is, don't worry about it, the record's in the cache, so it's going to be fast. Yes, it's going to be fast from the point of view that you don't have to wait for the disk drive, but you're still going to have to go through all the instructions, okay? So, and we'll see a little bit about how much it costs you as far as the instructions go. So if you look at it, you go from CICS to VSAM to SVC handler in the MBS side. We'll eventually send control to the input-output supervisor. The input-output supervisor will do its work, and eventually will do a start sub-channel and so on. The best place to see this next chart, okay, where you can see from your address space what's involved. You go and you issue your CICS read, and again, this is a very big I/O picture. There's a lot of things missing here, okay? But, you go into the stub will, in your program, will transfer you to control to CICS, to your execute interface program. That program will eventually figure out that you're trying to do a file control type access, and eventually it's going to get down that it's going to be a VSAM access, and turn control over to VSAM, which will analyze the request. And within that analysis, is going to say, let me see if I can find that record in memory, in this particular case, in our LSR pool. If it does, that's it. It stops right there and lets you continue with your program. If it isn't, then VSAM then has to prepare the CCWs, has to use virtual storage addresses, has to do a bunch of things, and eventually it's going to issue a supervisor call, which is going to cause a state change because it's going to create an interrupt. Then it's going to transfer control to the operating system, your MBS. The interrupt handler is going to say, "Oh, this is this is an SVC. Let me send it to the supervisor SVC's handler." Who eventually figures out it's really an IO type request. And there you'll get the supervisor to have to fix pages to do the IO, change the virtual address to real, all that sort of stuff. Eventually, it's going to issue a start sub-channel instruction. That's going to send the information of what you want to do to the path. As soon as the path receives the information, it returns control back to the supervisor, who will now say, okay, let me see, it hasn't responded, off we go. Comes back to VSAM. VSAM goes back to the dispatcher and says, okay, put this guy to sleep until we receive the record. In the meantime, out here in the hardware part, the command is sent out there, and if you find it in the cache, it's going to create an IO interrupt immediately. If not, it's going to have to wait. Then it goes out to the disk drive to find the information. So depending on on whether you have it in the cache or not, it's going to be a faster or slower type response. When you receive the IO interrupt, it's going to go to the interrupt handler in the supervisor, who will go again to the iOS and will schedule an SRB to indicate that the operation is completed. Once the operating system selects the CICS region to run, it dispatches SRBs have a higher priority than the TCBs. It'll post using an extended ECB, okay, and saying that the operation is complete. And eventually the dispatcher, if it finds that you're the top priority, the task with the highest priority, will automatically at that point dispatch you to continue executing. That whole operation, okay, and again, notice that when you get that IO interrupt, you're going to get yourself another state change as such. If you look at it, IBM, you can see down here at the source, the information I'm going to give you is in the performance guide on CICS TS 5.5. And you have the pages there, 176. In general terms, you're talking about every time you have to go physically out to the disk, forget about, whether it's in the cache or not, you're going to spend about 9.5K instructions to get the data for a KSDS or an ESDS. And RRDS is about 8.2. However, if you find the information in memory, and this is again from the IBM performance guide, okay, you will get, for example, on a read, it'll take you like 3,000 instructions, okay, for a KSDS, 2.4 for an ESDS, and 2.2 for an RRDS. Now, remember that this is for when you're issuing a read to a VSAM file, you're going to have, not only are you looking for the data, but you're also looking for the indices. So if you have a 3-level index, you're talking about 4 operations to get to the data. So that would be 4 times 3.0. Now, if for some reason one of those guys is not in the LSR pool, then you're going to spend 9.5 instructions going out to the disk drive to get it, plus the fact that you're going to be put into a wait state, okay? And I'm not going to talk about all of these, but you have them there. They're copied from the IBM performance guide, and you can find them there if you need any questions on that, okay? Okay. I'd like to take a few seconds here, a few minutes, basically, to make sure that we understand, and this is going to be basic for most of you, but just to be sure that everybody's on the same page, I'm showing here a 3-level index VSAM KSDS file. The lowest level of indices is called the sequence set index. You have one sequence set index for every control area you have in the file, okay? And as you look at this, these little green boxes will depend on what size of the CI that you have. For example, if you have a 4K CI, then you're going to get 108 of these little green boxes. Each one of those 108 green boxes has a high key. So the SSI has to have sufficient space to accommodate 180 high keys in it. Okay, now VSAM is pretty smart, and it has a compression routine from the index, and it not only compresses from the front part, looking at things that are duplicated, from one key to the next. For example, if you look at let's say a credit card file, you're going to find that everybody in the very beginning has the X number of characters, which are the same as you go down. So it would truncate from the front the like characters and would have only a one root index there. And from the back part, it eliminates non-significant digits. So it does a pretty good job, and IBM recommends when you start trying to calculate the space for this to estimate more or less about 1/3. In other words, if you have a 30-byte key, think that VSAM is going to be able to compress it to about 10 bytes. To that, you have to add the VSAM control, which normally can be from 3 to 5 bytes in length. Normally, if it's less than 255 CIs per CA, it'll be 3 bytes, okay? So you're looking at a 30-byte key taking up approximately 13 bytes within the SSI. So now, you will get one SSI for every CA that you have in the file, are maintained in sequence by a forward pointer. In other words, this guy points to the next guy, this guy points to the next guy. Now, if you ever have a CA split, suppose this guy has a CA split, you will go to the end of the file, look for an empty CA, okay, and move half of them. In general terms, it's going to be half of them, okay, to this last position. But now you have the file out of sequence physically. to maintain the file, they do it logically. What they'll do is they'll change this pointer to point to this last guy here, the sequence set they just created, and then this guy, instead of pointing to the next guy, will point to the one that was, was originally in sequence. Okay, so that's the way that it'll work. Now, the other thing which is very important about this thing is this looks like a nice little structure, but it really is a flat file. And the way it maintains the sequences here is not only using horizontal pointers, but it also uses vertical pointers, okay? So, and the other rule which is very important is when you have two indices at the same level, or in other words, when I get sequence set 0 and sequence set 1, when I have two at the same level, I have to create a boss. The moment that I have two of the same level, I need a boss, and that guy will now control all the sequence set indices until he gets full. When he gets full, in other words, he doesn't have any more space for more keys, he will create a second guy. Now you have two guys at the same level, so now you have to create a boss. Okay? Now, that's the way that VSAM is, and these basically have RBA pointers, and it tells you now who's the top guy. The catalog, the index that you have, it points to, if you look at a list cat, you're going to see that it points to the high index set record, okay, as such, okay? So this is generally how it works, and you have two measurements out there which are very important. One is the HERBA, high used RBA, and the other is the HARBA, which is the high allocated RBA. The high used RBA is how much of the file you're using at this point. And the HARBA is how much you allocated, okay? So you, in a file, you may want to have, let's say it's something like 80%, 80% used and 20% for growth, okay? That sort of thing, but that depends on your installation and your standards, okay? And it also depends on your knowledge of the files that you're going to be using. Okay, so in general terms, this is what we're going to be talking about, the sequence set index and the index set being the second level and higher. You normally do not want to have more than 3 levels, okay? If you have more than 3 levels, and I'll talk a little bit about that at the end, what can cause that sort of thing, okay? And you have to watch out for that, okay? Any questions so far? Okay, if not, I've always talked about, when I talk about tuning LSR, I always talked about Robin Hood. And those of you who don't know about Robin Hood, you're not old enough, I guess, to watch all those old pictures of Robin Hood and Sherwood Forest and so on. But Robin Hood, his claim to fame was that he would rob from the rich and give to the poor. In LSR, it's the other way around. You're going to rob from the poor to give to the rich. Who are the poor? The people who don't use LSR very often, and very low activity files. So you're going to take advantage of them participating and giving you, putting in their buffers and strings, but the guy who's going to get the best benefit is the guy who's more active, and so on. So most of the best contribution that is made by a low to medium activity file to LSR is to provide their resources for the more active sort of guys. Now, let's go into what the traditional tuning is all about. Okay, the traditional tuning.
Can I interrupt you there?
Sir.
I've got a question from Alan Winston. He says, big picture question. If a VSAM file is NSR and is within a DFSMS data class that specifies system managed buffering with direct optimization, it would seem that it would be logic similar to LSR, though a black box in terms of the buffer sizes chosen.
The question is very good, but I think it applies more to bash than to LSR. In other words, the DFSMS is not going to work the same way in the NSR under CICS. Okay, but that's a good question. I'll just to make sure, as soon as Trevor, if you can send me his email, I'll do some research and get the information back to him. Okay, but I believe that's only for NSR running in batch. Okay.
Yeah, he does. Does this work within CICS? If so, what are the trade-offs versus LSR? Okay,
well, the trade-offs are basically the look aside. Okay, what we've seen basically when you use NSR files is the only look-aside that you have as far as the sequence set index is if you happen to get the same string assigned to you and it happens to have the same sequence set index already in there. In other words, there's no look-aside to the other buffers assigned to the strings. Okay, now that's a little bit different from VSE, by the way. VSE is superior in that sense. But MBS, you don't have that look aside from one string to the other, okay? And that's really what's going to happen is that you're going to wind up with about a 40 to 60% look aside versus in LSR where you can get up in the 90, 95% type look aside, okay? And I'll talk a little bit more about the objectives and so on, and every installation is different. But if you can send me his email, I'll try to do the research on the other part for him, okay?
Okay, I will do that.
Thank you very much, Trevor. Okay, the other thing that the basic things, again, this is the traditional tuning that we're doing today. And that basically is, first of all, is how do you define your LSR pool? Your LSR pool is either a static definition or a dynamic definition. Dynamic means that you don't do anything. You just let the CICS read the files as they come in, and dynamically it'll create how many buffers it's going to require and how many strings it's going to be using, and also it'll determine the largest key length that you require. Okay, so you don't really have to do anything. It's quick and it's simple, and you don't have any risks. Now, if you do the static definition, okay, the static definition has the advantages that you, first of all, is that you can define a separate data and index pool, okay? So there will be no contention between files, between the data CI and the index CI, which is something you want to try and avoid. Now, in some installations, they set up some rules that say, look, I'm going to reserve 512, 1K, 2K, and 4K for index CI sizes, and anything above 4K is going to be for data CI sizes. But that's hard to implement because, in many cases, the systems programmer does not have control as to what the application requires. But if you can do it, that's a way to get around that, okay? The other thing is that you can do with static definition is that you can optimize. In other words, when you do the dynamic definition, you're just going to get X number of buffers, based on a percentage that's given. And usually, if you want to make it a real simple thing, I mean, you can read the book and it'll give you how complex it can get. But in general terms, it's the number of the number of LSR strings that you define. The number of strings you define for the file. 50% of it, okay? So if you define a file with 10 strings, you're going to get 5 data buffers and 5 index buffers, okay? Now, in that case, it doesn't, you don't take into account that file may be very heavily active or maybe very low active. So in other words, you don't get that sort of choice there. But when you do your static definition, you know which files are more active and you can allocate more buffers to it. Okay, you can also optimize the string and maximum key size. And we'll talk a little bit about that benchmark that we did on that so we can show what it costs you when you start changing the number of strings and the maximum key size. The other thing is a faster initialization because since you have to define the key length, you have to define the number of strings, and you have to define each individual buffer, how many you want. Well, that's easy to do, for CICS to go ahead and allocate it. But if you don't do that, in other words, you're doing dynamically, then CICS will have to open each file, okay, and determine what the numbers, what the size of the CI is and so on to be able to determine what's going to read, and also needs to determine what the largest key is. So it's a slower type initialization when you have a dynamic definition. The other thing is, and I'll talk about hyperspaces because this is something which is hyperspaces are not supported directly as like it used to be in the old days, because hyperspaces were designed for expanded storage. And expanded storage is not available in ZOS or in the Z architecture as such. Now, the disadvantage, which I've already started talking a little bit about them, is that in the dynamic, there's a possible contention between the index buffers and the data, because it's just one pool and it can hide data or index performers, because you don't know, how well the data is or how well the index is doing. Okay, specifically in those CI sizes where they can be the same, like 4K or 2K and so on. Okay, also, as I mentioned, the number of strings and buffers are allocated on a percentage. 50% is the default size, and it can result in a string over allocation. Okay, slow initialization because you have to open each file to get the information from it, and that you need. How many strings? Not so much. Well, not so much strings, but how many buffers you had allocated, and so on. And you cannot allocate hyperspace buffers, okay? The disadvantage of the static definition is it requires systems program intervention, and you're exposed. You have to make sure that, you do a good job of determining which buffers you need, okay? So it requires planning, and, there's a possible solution, which some people just go ahead and do, and that's they just define the maximum 255 strings per buffer pool. Okay, and they say a maximum of 255. And I'll show you what that costs, because I was surprised myself when I did this benchmark in CICS TS55 on our system. Okay, so any questions so far? Okay, so the recommendation is that we do define the LSR pools explicitly. And if you're starting from scratch, the best way to do it is to first open it dynamically. Dynamically, with your performance monitor or your stat transaction or your end of days transactions, you can see which buffers are allocated, which are needed. And if you put a little bit of people using it, you'll be able to see which ones are the ones that are most used and so on. So you know that you have to allocate more buffers to that. And in addition to that, at first you won't be able to tell how much you need for the index, because they could be mixed. In other words, both of them could be accessing the 4K. So what you do is, after you open it dynamically and you see how many you need, you duplicate the index portion of it, okay, with the same buffers that you have for the data, and then you run the information, and you'll get the statistics, and you'll see which buffers are really used by each one. I can't tell you that, forget it, after 8K, nothing happens, because I've seen people who go in and define, let's say, a cluster, and they put the CI size that's required for the file at the cluster level, not at the data level. So you can wind up sometimes with somebody asking for a 26K or 28K CI size, not only for the data, but also for the index, because they put it in the wrong place. Okay, so that's something you have to watch out for, and that's why I say you define them both with all the buffers that you have, and then you see what activity you have when you run it. Once you have that information, then you start tuning it, eliminating those that you don't need, increasing those that you want to, and and off you go. Okay, and again, once you're in production, you monitor and adjust as required. Okay. Pool measurement. Now, every installation has, their own objectives. In general, most people say that they like to get an 80% look-aside hit on the data component. On the index component, they like to get a 95% and a combined of 93%. In other words, that you only have to go to the disk. If you meet that 93%, you're only going to the disk 7 out of every 100 IOs or requests that you did. Okay, some installations have higher objectives, some don't have any, and it just depends on what's acceptable for your installation and what guidelines you set. In general terms, it's a lot easier and a lot better to try and improve the index component first, for many reasons. One is that you have less index records or CIs than you have for data. And in addition, most indices are smaller in size and the number of bytes it takes than the data. So you don't need as many resources, virtual storage and real storage, to tune that part, versus like you do for the data side. So try to improve first your index. And remember, in general terms, a 2-level and a 3-level index, which are quite common, especially for your big files. Okay, you're talking about, out of the 3 IOs for a 2-level one and a 4 IOs for a 3-level one, 75% or 66.6% of the time is the access is going to be to the index. In other words, the data is just the last portion of it. Okay, it's just one up on it. Okay, so data buffering tuning, which is, as I mentioned, probably the hardest part of them all, because it's going to require it usually requires a lot of virtual storage and real storage to get that 80% hit ratio. And most of the time, the best way is the files that have sequential type activity, or have the read for update, rewrite, delete activity, or a concentrated activity. You know, the browse type files and that sort of thing do quite a bit to help improve the leukocyte hit ratio. Okay, now something which is very important that we understand is that just because the 4K buffer is that I'm getting a 95% leukocyte hit ratio, that does not mean that every single 4K file is getting the 95%. Some of them are going to get a better response, and some are going to be getting less response. That's the average of all the files that are executing. Okay. So, you know, you have to be careful because, you know, don't reach a conclusion that says this file's okay because it's getting 95%. That file could be getting, you know, 80% or 82% because he's not as active as the other files that are in the pool. Okay, buffer allocation, okay? One of the things which is very important is that a lot of installations, to avoid that problem that I was mentioning that you forgot the one particular buffer size or something. Well, some installations say, I'm going to always define buffers for the 11 buffers that are available in LSR. The problem with that is that you're going to allocate virtual storage that will not be used day in, day out, 365 days a year. Okay, so for example, suppose that you have this particular case that you don't have any 16K data sets that you will use that 16K buffer. So, but if you're going to use this philosophy, you're going to allocate a certain amount of storage for the 16K buffers, even though nobody's going to be using that storage. Okay, so what happens basically is, how much do I allocate? Well, do I allocate 100 buffers? Do I allocate 3 buffers? Do I allocate 10? You know, you have to make a decision. That's not a magic number. You know, it's just something you're going to invent. It's very hard for you to say, you know, how much that new file, if it ever comes in play, is going to require. Well, in general terms, I personally prefer to do something else. I would take that 640K, which would be, in this particular example, 40K at 16K, 40 buffers at 16K, which would be 640K. And I would allocate it to the next CI size, which would be, in the case of 16K, be the 20K buffer. So if I take 640 and I'd say divided by 20K, I would increase my 20K buffers by 32. Now, that's going to be used day in, day out, okay? And if someday, by some accident, you know, I define a 16K guy, well, he's going to fall into the 20K in the meantime, but I had allocated whatever I was going to allocate for him anyway. It's there, okay? So it's something, you know, you can think about. Again, a lot of that depends on how much virtual storage you have available. My philosophy, and then, again, everybody has their own, is I'm going to try and avoid as much as possible to have resources that are not being used when I can use them for something else can be more productive, okay? Okay, the other thing which is important to understand is that the number of buffers that a file can take and get is not controlled by what you defined in the definition for it in the file control table. In other words, you can have a file that you define 20 buffers for, as far as a buff ND goes, but you can wind up with basically that guy using 100 or 200 buffers, depending on his activity. So a file can have more buffers assigned than what you defined in the file control definition. Okay, the other thing is string allocation. Each pool can have up to 255 strings, okay? And you normally tune it when you get a short on string condition. There are 2 types of weights that are associated with an LSR pool. One is a weight on string dedicated to the file itself. In other words, the file went short on strings. The other type of short strings that you can have is that you use all the strings you allocated to the pool. Now, it's very important that we understand that the control of strings in CICS is done by CICS. In other words, CICS is the one who controls it. In other words, if I went out and I asked for I only had 5 strings and I asked for a 6th string, vSAN would dynamically allocate another one, which would expose me to having a get main failure if I run out of storage. So CICS will allocate this and control the strings for you. Okay. Okay. Now, in general, the objective I like to use is that I want to have, if I have 100 strings, okay, allocated, that means that the peak number of strings that I'm going to be using is between 50 and 60%. That gives me the capability of being able to, in high volume activity, to be able to have a 50 or a 40% growth factor on that. Again, that's something that you have to decide how you want that done. Okay, the maximum key size that you have available, okay, is 255. And the reason this, since the control blocks are shared, you need to determine what the maximum key length, because the PLH, which is the placeholder control block, has to have space for the key that you're going to access. So when you say that I want 128 bytes for the key length, that means you're going to reserve 128 bytes for every string that you allocate in the pool, okay? Because it needs to have the maximum length. Okay, if you don't have that, if you try to open a file does not have has a higher key length than the one you specified, that file will not open in that pool. Okay. So in order to avoid that, many installations define that the maximum key is 255, and then you can forget about it. But there's a cost, and the actual cost depends on how many strings you have allocated. And again, we did a benchmark on this on our system. Our LSR Pool 1 had 60 strings and a maximum key length of 100. And we decided that we wanted to see what the effect was if we had raised our key length to 255 and the maximum strings to 255. In other words, we're adding 195 strings and we're adding 155 bytes to the key length, okay? What we did then is we brought the system down, okay, and we brought it up. It's step 1 and step 2. Step 1 was with the current settings of 60 and 100. The step 2 was with 255 and 255. And we looked at the amount of storage that was over when we did this step. When we initialized, we found out that we had 856 meg of storage available with our original definition, but with the other definition, it would turn out to be that we had 856 itself, but it was 352K less. Okay. Now we open all the files. Okay, and we wound up with these same numbers you see here, but the difference was 588K. Now we had estimated. We said, okay, we're going to have 195 strings, and we're going to have 900. We have 900 PLHs. Such the whatever it was, it comes out to be 175,000 bytes plus 195 strings times 155, which is the key length. It turned out to be. Now, 900 bytes is the size of the PLH. It's a little bit bigger, but it's approximate that, so it makes it easy to multiply. The sum was 205,000 bytes, and it actually turned out to be a lot than we had expected. Again, you need to do that sort of benchmark on your installation. Now, the difference is there are some control blocks that are built after the file is open. Things like, for example, the number of extents that you have. Not only do you have and I'll talk a little bit about this at the end of the presentation. Not only will you have some file, what do you call this? Some cost of the extents, which are about 20 bytes per every extent. Excuse me, 32 bytes, X20. But you also have an index that's created for it, able to do sort of a hashing type technique. So it get affected by having 123 3 extents on a disk. Okay. So that's one of the things you need to look at, the cost of when you use 255 and 255. An area that must be monitored is a part of a buffer monopolization. Again, the problem is that what statistic did you use to say that a file is monopolizing the buffers? You don't have a statistic. All you have is an activity. So what does activity tell you? It tells you that I did 100,000 requests, but that doesn't mean that I'm using 100,000 buffers. Okay, I could be doing 100,000 to one buffer, like I could be doing 100,000 to 20 buffers, or to 50 or 100 buffers. So there isn't a statistic available for you. Now, what I have found in my case, not that to use the IBM or the traditional type environment where people say, okay, move that that file to a different buffer pool. Okay, the problem again is if you do that, those resources are not going to be shared. So, and if that file has activities that are low volume, those resources are not there. What I found is to go ahead and increase the number of buffers. And I kept increasing the number of buffers until it gets to the point where that file reaches its point of diminishing return. In other words, you can give it more, but it's not going to use more because it's already reached its point. Once you reach that point, buffers that you add will be used by the other files in the pool. And again, the LRU algorithm works better, the more buffers you have available. Okay. Now, what happens if you need that a file and you forgot to put a specific buffer or the max key length is not defined? Well, you have several alternatives for that. I always recommend that you at least allocate 3 to 10 buffers of 32K to make sure that you always have the proper size. The other thing that you can do, and this is in the case that you have a key length that's not defined, it's bigger than the key length that you have, is open that file. When you try to open it, it's going to fail on you. So what you do is you say, okay, it was trying to open it in pool 1, I'm going to assign it to pool 2 and open the file dynamically. When you open the file dynamically, one of the other changes I make is I put 255 strings to it, so that at 50% it allocates more buffers at least than I was going to get there. So that's an alternative that you have. And again, the other alternative is to go ahead and define the 255 that we already saw. If you have the memory, you have no problems with that, okay? Hyperspace buffers. Hyperspace buffers, as I mentioned, were designed for expanded storage, and basically it was a fast synchronous paging device. Expanded storage is less expensive than real storage, and ES was addressable in 4K bytes. In other words, you couldn't byte address it. Okay, so in other words, the transfer is always 4K at a time. Z architecture does not support it, but IBM, in order to maintain the function on it, basically it says, okay, I'm going to dedicate real storage to that expanded storage hyperspace. But it's going to work the same way as it was. In other words, you move it out from real storage to real storage, and then from real storage back to the buffer pool. So you're paying a price of CPU time, okay, of being able to do that. So, and if you have the real storage available because you already had it defined, then what you do is just merge those buffer definitions into your normal LSR definition, and there you are. You eliminate that real storage move that you don't need, okay, the overhead. Now, there are some reasons you may want to use hyperspace buffers. One is, what happens if I need more than 32,768 buffers? Okay, well, you can basically then use hyperspace buffers for it. The other thing is, what happens if I'm running out of virtual storage? Okay, suppose I only have 30 meg or 20 meg and I need left on the virtual storage. I can't expand my buffers. So what I can do is allocate expanded storage buffers, which are not part of their virtual storage availability in the region. So that's something which is important, and one of the reasons why you may want to use hyperspace buffers. Again, remember there's an overhead to it that you may not pay, but again, you may have some reasons for it. Okay, other things, we have fragmentation. One of the things which, let me just show you this chart here a second. vSAM has 28 different CI sizes, LSR has 11, Hypercache has 8, and vSAM RLS has a total of 16. So whatever you have, for example, fragmentation, whether you want to or not, 1.5K is going to use a 2K buffer, 2.5 or 3K or 3.5 is going to use a 4K buffer. So this is the type of fragmentation you need to look at. There are some that you may want to do. For example, an 18K CI size for the data has a 97% utilization on the track. which is the best. So if you need to get, you're running short on space on disk, an 18K CI size is good, as long as you're not using vSAM expanded. Once you use vSAM expanded, then the problem is that IBM will put a 32-byte trailer onto the 18K, and no longer will you be able to fit 3 records of 18K on a track, and it converts it to 6K records, 3 6K records to be able to do that. So you lose, you go from 97% to about 87% utilization. So that's something you have to be careful when you have an expanded storage. I mean, you have, let's say, a 18K CI size using normal vSAM, and then you go and you put it as vSAM extended. If you don't alter that 18K, you're not going to get the same utilization on the disk. Okay, now, anyway, so you see that there's some fragmentation you may want. For example, an 18K gives you the best utilization on the disk, but you're going to suffer 10% loss of real storage and virtual storage fragmentation. So it's a trade-off. Which one is it you need most? Is hurting the most? Is it space on disk, or is it the memory and virtual storage? Okay, now there are some fragmentations you don't want to accept. For example, suppose somebody had a 10K CI size and you didn't define a 12K buffer. Well, it's going to use the next larger one, which in this case may have been a 16K. That sort of fragmentation you don't want, okay? So that's just the sort of thing that you want to look at and when you have your files out there. Also, there are some files that you may have, for example, 5.5K, okay? There's a couple of packages that use this, 5.5K. Now, the problem is that LSR is going to use an 8K buffer. That's a loss of 2.5K, 31%. In many cases, you can raise that CI size for that file to A. It takes advantage of being able to adjust your free space without increasing the amount of virtual or real storage used by LSR, because you're already using 8K, whether you're using 5.5 or using the 8K. So that's the sort of thing you may want to look at. The other thing is, in the index side, it's also very important, because, for example, a 1.5K index CI size will be using a 2K buffer. Now, for large files, going in there and saying, I'm going to go from 1.5 to 2K, and again, let's look at this thing here. If this guy had space for 180 CIs, as high keys, because you had a 4K CI, then this guy approximately should be able to accommodate 180 of them, right? Well, the problem is that 1.5 may be fine, but at this level, if I raise this to 2K, number one, I'm only going to use what I needed. I may wind up with 512 bytes that I didn't need, but this guy will be able to accommodate more SSI buffers in here, high keys, and therefore reduce the number of index records that I have. Okay, so this is one of the advantages you may want to take advantage as far as increasing the sizes to what you're already going to be paying, as far as you're already using a 2K or a 4K buffer for this type of thing. Okay. Okay. The other thing is you have to be very careful. Okay, especially with a lot of people, and even the books recommended that you let vSAM determine the CI size for your index. The problem is that sometimes in very large files, you may wind up with a large CI size like 28 or 26K, and it results into a 0.5K index record. The problem with that is that if that file is very large, you're going to go into a lot more index set records, that second level or more records. And if you raised it up to 2K, you would reduce the number of that. Now remember, each one of these guys has to have a buffer to be able to be allocated in there. So you want to reduce the number of these guys to make sure that they don't, you can use it for these guys, for the sequence set and everything else. Okay. So far. Okay, this is a minor thing. It's just to let you know, if you have a 0.5K buffer, okay, vSAM always allocates in multiples of 4K. So if you say I want 10 5K buffers, okay, 0.5K buffers, you would wind up using only 5K of the 8K, and you wind up losing 3K. So make sure at these small levels that you have a multiple. In other words, if you have a 5K, 0.5K buffer, make sure that what you allocate is in multiples of 8, multiples of 4 for 1K, and multiples of 2 for 2K. So you take advantage of getting extra buffers without paying any additional price. Okay, number of LSR pools. There's a lot of people that talk about this. They say, some people go with 1, some people go with 2. Okay, the main thing which is important about the number of pools is first of all, it's going to take a little bit more memory, but in addition to it, the LRU algorithm works better when you have a bigger number of buffers and everything to work with. So, you really should try as much as possible to consolidate everything to one pool. The only time that you really would be justified to be able to take more than one pool is when you use vSAN ThreadSafe, because vSAN ThreadSafe now will be able to access the different LSR pools using an L8 or an L9 TCB. So you'll be able to run in parallel to getting to access. In that case, now you have to sit down and see which pools, which files you're going to define in the different pools so they can have separate access. You have 255 of them, so you have plenty of spaces to be able to distribute that cost. And the question is whether you've gone to vSAN ThreadSafe or not. Okay. Again, 255 pools are available. Remember that LSR is shared. In other words, whatever you have, the more pools you have out there, okay, what's going to wind up is, you're going to wind up with possibly pools with files that are not very active at certain points of the day, and you have resources that are available, but they can't be used because they're in a separate pool. Okay. Now, there are some cases you may want to have some, okay? I already mentioned the bottom one, which is a vSAN ThreadSafe. The top one is the one that you have to look at very carefully, and that is data tables. Data tables, you're supposed to put data tables basically in an, you're not supposed to have data tables that have 90% or better read activity, okay? That's what you want to have. The problem is if you have a data table that has to go to do an I/O, does a read, it does a write or does a read for update, that sort of thing, you're going to go to the original file and you would go through the LSR. But the problem is data tables at 90% activity probably will not have their indices and their data in the LSR pool, because the other files are going to be taking whatever they had. So you may want to put all your data tables in a separate pool so they compete only with themselves, okay? Okay. What files should not be in LSR? Share options file, never into LSR pool. Why? Because direct reads requires the reading of the CI from the disk, ignoring the fact that the CI is already in the buffer. The other files that don't follow the command level guidelines, which the example which I gave is start browse, read next, and then after a while you say read for update without doing the end browse. That's going to cancel, okay? But you shouldn't have that sort of condition. So those type of files, either you correct the browse condition to do an end browse before the read for update, or you put it in NSR. High files with high CA split activity, you may want to put those into NSR, but again, the way NSR uses its buffers, only the first guy gets the buffers, okay? So those are some of the things you may want to. Some hidden tuning areas, the CA size, okay? CA size is again, remember, the sequence set index handles the complete control area. So CA size can be in what's called track managed storage, is basically the normal vSAN that we have. It'd be 1 to 15 tracks would be the CA size. How you determine the size is usually by what you allocate in the primary and the secondary. Because the important part, which I need to reemphasize here, is CA size has to be the same size when you go from the primary to the secondary. In other words, you can't have a secondary that has a different CA size than the primary. So, and there's no parameter that you can say, allocate, my CA size should be this size. The way that vSAN decides is based on how you define your secondary and primary allocations. Okay. And the other type that you have is called cylinder managed storage. These are terms that come up now when you have more than the 64K cylinders for the new large disks that are available. In that case, the allocations are going to be done in multiple cylinder units of 21 cylinder allocation, 315 tracks. And the CA size has to be a multiple of 315. So these are the different sizes you can have for that. 15 tracks naturally will be a cylinder in size. There are some cases where you can have a 16 track type CA, but that's some special cases. In general terms, cylinders will, if you allocate cylinders, it'll be one cylinder. You allocate in tracks, you have to be careful with the highest common denominator, and I'll show you some examples on that. And be careful when using records, which can lead to a bad CA size. Okay, for example, if I had said, and I'm going to show you another example to show you how bad that this can be. If you're going to have something in tracks, always make the primary equal to the secondary. That'll guarantee the largest CA size. In other words, I have 7, and if I go to a secondary, it's going to be 7, so they're the same size. Okay? Now, the thing I mentioned about records is that the way that it determines the size is it uses the average record length. How many people know what the average record length is for a variable length record, a variable length file? Not very many. And the problem is you specify it and BSAM doesn't update it. It just stays there. Okay? So you have to be careful when you use the records type environment. Now here's an example. If I did tracks equals 3, 1, and I basically fill up all 3 tracks, I'm going to generate this type of structure. I'm going to generate track number 1, because remember it has to be the same size in the primary and the secondary. So I'm going to generate for one track a sequence set record, for the second track a sequence set record, for the third track a sequence set record. Since I have 2 at the same level, I need a boss. So I'm going to generate for a very small file, I'm going to generate 4 indices, okay, a 2-level index out of a file which is, is nothing, okay? Now, if you had defined this file as 3.3, you would get 1 sequence set index for the 3 tracks, okay? So this is very important that you look at that, and especially in those small files. Okay, CI and CA splits, again, the good part is that VSAM doesn't cancel on you by having, or it can, but in general terms, it'll continue to operate. The bad is that you have extra I/O operations, okay? Especially when a CA split, which splits 50% of your file normally to another area. And the ugly is, suppose that I need now a new CA and I'm run out of space within the space that I've allocated. So I have to go out to get an extent. Okay, and getting an extent involves going out to the catalog, updating the catalog, the BVS, and the VTOC. So it can be a long operation and depends on the activity that's happening in the system at that point. Okay. Also, CI and CA splits can create free space that cannot be used. So you can get yourself into a place where you've taken so many CA splits or CI splits that you have a lot of free space, and the file is big. It takes longer to process, but you can't do, unless you reorganize, you're not going to recover it. Okay, now there's a hidden cost to CI and CA splits, which is not normally discussed. The thing is, suppose I had a CI before and I only had 1 buffer for it. But the moment I take a CI split, I need 2 buffers for the data, okay? To get the same amount of data, okay? So splits, CI splits, you have to be careful. When you get these files that are 2,000, 4,000, type of CI splits, you have to think that you're going to be having buffers, additional buffers out there with only 50% full, okay? So that's a hidden cost that you have there. And CA splits can also cause you problems because CA splits can also result in index splits. And those also will require additional buffers for it. So you want to maintain, the minimum number of splits as possible. And again, it's the free space that's allocated, that's your best defense. And reorganization Maybe. Normally, I recommend that you reorganize a file when you have when the CI splits represent 30% of the file. In other words, if you look at the total number of CIs in the file, and then you say, suppose there's 1,000 CIs in the file, and I have 250 splits, then you're talking about 250 over 1,000, you're talking about 25%. When that number reaches 30% or the CA splits reach 30%, I normally recommend that you do that. The other time that I recommend it is when your total free space within the HERBA, the part that you're using, is greater than 30%. Because that means that you probably have a lot of free space out there you're not using or not going to use. Okay, the last thing we're going to talk about is extents. And again, extents, IBM has made some tremendous improvements in this area, especially if you have space constraint relief, and that's with DFS-SMS. You can have up to 123 extents per volume. You can get up to 59 volumes times 123. So you can get a file that can have up to 7,257 extents. In addition, IBM has extent consolidation, which is if you wind up with an extent, the next extent contiguous to one previous one, it'll consolidate it and won't add one to the total. Okay, now, again, the data set, anytime you have a split and you get one of these, the data set will be serialized, okay, for this. And again, anytime you go to extent, it's going to cost you quite a bit of time, okay, and the file is going to be, inaccessible by other people until it's completed. And most of this information, I have to thank Ms. Terry Menendez from IBM, who does a lot of the presentations at SHARE. That has to do with SHARE and the IBM University that have to do with the RLS and so on, VSAM. Okay, so extents, you want to reduce as many as you want. And again, what does an extent talk about? You have basically three things. You have an extent definition block called an EDB. You have a header and then hex 20 for each extent in there. And you have a logical physical mapping block, which gives you some other information. And if you look at that, this is what it would look like. If you look at let's say a list cat, you find out that this is the starting RBA and the ending. And I underlined this guy just to show you how it's calculated. You have a total of 8 extents in this file. When you look at memory, this is the extent, this is the header out here. Okay, it tells you have 8 extents. The extents are 0, 1, 2, 3, all the way to 7. And what it does basically, it tells you this is the extent 0. And now remember, I looked at this extent, which would be from cylinder 51 to cylinder 51E, and it starts at 9. The RBA is 926000. So how do you get to that? If you go here, this is the second extent, which would be number 1. This is the cylinder where it starts and where it ends, and then this is the relative CI number 12C. This particular file is 30K. Okay, so it's 7,800 in hex. So if I multiply 12C times 7,800, I get 8C000, which is 9216000, which is what you have here. Okay, so that's how the extents work. Now, it used to be you look at this sequentially. Now they create sort of like a hashing technique for it to make it run as best as possible. As fast as possible without the overhead. One of the things that you have, and this is something which is very important as far as extents goes, is don't be meek asking for the secondary. Okay. Remember, every time you take an extent, your CICS is going to be held up. That file is going to be held up until you finish the extension. And don't do this type of thing. Ask for 200 cylinders and then 2. If you're going to do that, if you're going to pay the price of having to go out to update the VTOC and the BBDS and the catalog, ask for something that you can spread this across some more time. Okay, and again, make sure you reduce the number of CA splits by having the proper. Or you're not going to eliminate them, but you can reduce them. Okay, and here's an example of a simple thing. The free space works quite a bit better when it's bigger, and this is my own experience, but yours could be different. The bigger the CI size is, the better the free space works. Here's one where you have a 4K CI size that results with a 25% free space, 25 times 4096, 1024. In other words, you're going to have 180 records per CA. Okay, so in other words, you're going to wind up with saving up, some space as such. Okay, getting 180 records available within a CA, one per CI. Okay, if you have a 1,000 byte record. Okay, now if you change that to a 25 to an 18K and you reduce it to 22%, you're going to get the same amount of records. Okay, but the difference is the amount of space you require. Okay, the amount of space you require, okay, this is the formula for fixed length records, is the CI size minus the free space you're requesting, minus 10, which is the VSAM and control information, divided by the record length. So you get 3 records per CI, okay? So 100,000 records by 3, you're going to need 33,330 CIs. You can fit 180 of them into 180 into the cylinder, into the CA. That gives you 186 cylinders you're going to need for the file. You do the same calculation, and you get that's going to be 159 cylinders. Okay, you save 27. Not only have, I think, better free space use, but save space. Okay. Due to its better LucasI capability, I recommend you use LSR over NSR as much as possible. Tune buffers to LucasI hit ratios. That's basically your installation dependent. You should look at your LSR statistics anytime you make application changes. You should look at those LSR statistics. I normally like to look at those at least once a month to make sure they're running right. And again, LSR involves, part of the tuning for LSR involves the CI size, the CA size, the free space, and the extents that are allocated to the file. Okay. Any questions?
Okay, we do have a comment that came in a little while ago from Alan Winston again. He says, an application technique that can reduce splits if the key pattern matches the requirements is VSAM mass insert. Comment on that?
Can you repeat that? I didn't get the question.
Sorry, he said an application technique that can reduce splits if the key pattern matches the requirements is VSAM mass insert.
Right. Okay. That's a good. Basically, if you can getting yourself to add things in the mass insert, which is a sequential type addition, that'd be perfect because you reduce that. However, you have to think about that. Not every file you have the capability of being able to do a mass insert. Now, most of the files that you see online are usually direct additions. In other words, not really a mass insert type deal. But it is a good point that if you do mass inserts, you do reduce the what do you call this, the CA splits type on there.
I'll just give people a minute or two to type in any questions if they've got them. I know we're running quite late now, so I won't wait too long. If people do have questions for Gene, they can always send them to me, and I'll give you my email address in a moment.
My email is on the front of the cover of the first page.
Right, brilliant. So you can email Gene. Like I say, a copy of his slides will be on our website later on today. All right, I think I will move on because of time. So can I thank you very much, Gene? I thought that was a fantastically fact-packed session. That was amazing. So because we're a virtual user group, can you assume that you're getting a virtual round of applause?
Thank you very much for the opportunity to participate. I hope people got something out of it. Okay.
Thank you. I'm just going to make me presenter again, so you might get a message on screen.
No problem.
Let me just share. Right, fairly quickly then, let's go through some things. The news then is that IBM has announced new automated unit testing capabilities for CICS COBOL programs using DB2 with IBM developer for ZOS, better known as IDZ, version 14.2.1. What they say is that users are now able to stub out CICS DB2 calls for COBOL programs through the enhanced record and playback functionality, as well as export results in new formats. Automation of testing is a key component for agile development, and there's a link to that story on our website. There's only been one article, and that was back in September. That's CICS Library is now available in Maven Central, and that was by Nina Ben Cox, and that's on the CICS Developer Centre site. Yeah, as always, you can send me your feedback about this meeting. You can either use the Contact Us webpage on our website, or my email address is on screen at the moment, trevor@itech-ed.com. Right, coming soon. So, when Rocket Software took over this user group from Fundy Software last year, they also took over sponsorship of the user group. However, they've just let me know that they've decided to no longer sponsor it. And that means, as a user group, we're looking for sponsors in order for the group to continue. So we're looking for someone to host the 10 years worth of files on their website and provide access to WebEx or something similar to host these meetings. So if you want to find out more about sponsorship, or if you've got any vendors coming to your site in the next little while and you can convince them to sponsor us, then get them to contact me at trevor@iteched.com. If we do have a sponsor, then our next meeting is on Tuesday the 14th of January next year, when Ezreal Gross will be speaking. Sadly though, if we don't find a sponsor, then this will be the last full meeting for this user group. Yeah, just a reminder that you can keep up to date with what's happening with CICS and the CICS virtual CICS user group by following us on our website, Facebook, on Twitter, on LinkedIn, and if you do tweet or anything, the hashtag to use is virtual CICS. And we always like likes, so if you can go to our Facebook page and like us, that would be great. Okay, well that's all for this meeting of the virtual CICS user group. And I thank you all for attending. I thank Rocket Software, who sponsored this user group for the past year. As I said, if your company would like to take over sponsorship, please let me know. And I'd particularly like to thank Eugene Hudders for today's presentation, which was brilliant. So that's it. Thank you all very much for joining the meeting and for your support over the past 10 years. And hopefully this group will meet again in the new year. So thank you all and goodbye.